Hello everybody, my name is Ethan. Welcome back to the channel where today we are going to be hopping in back to our machine learning class on Codecademy. In the previous episode or video that I did, we finished out the chapter on k-nearest neighbor regression. In the previous two videos, we were talking about k-nearest neighbors as a classifier and then also as a regressor. So there were two videos on k-nearest neighbors, and we're kind of in this huge regression section where pretty much that's all we've been doing. We're going to continue that with something called decision trees. So we'll hop right into it. Stop wasting your time here. What is a decision tree? Decision trees are machine learning models that try to find patterns in the features of data points. Take a look at the tree on this page, which is obviously this right here to the right-hand side. This tree tries to predict whether a student will get an A on their next test by asking questions like, what is the student's average grade in the class? The decision tree tries to get an understanding of their chances on the next test. In order to make the classification, the classifier needs data points with 4 features, such as their average grade, number of hours they study, number of hours they plan on sleeping the night before the test, and whether the student plans on cheating or not. So, for example, let's say that somebody has a B average in the class, studied for more than 3 hours, slept in less than 5 hours before the test, and doesn't plan to cheat. If we start the top of the tree and take the correct path down the beta, we'll arrive at a leaf node that predicts that the person will not get an A, right? So we'll say our current grade is a B. We are saying that the hours studied, we said, is less... studied for more than, how many hours? Slept less than 5. We're going to say they studied greater than 3 hours, and do they plan to cheat on the test? No. So, we have a prediction, no. If we plan to cheat on the test, yes. What ends up happening still says no, right? If we say we have an A average in the class, and we say that we're going to study for more, and more than 3 hours, it's looking like we have a good chance of getting an A, right? So that's how a prediction tree or a decision tree might work. So what is a decision tree? Continued. If we were given this magic tree, it seems relatively easy to make classifications, but how do these trees get created in the first place? Decision trees are supervised machine learning models, which means they are created from a training set of labeled data. Creating the tree is where the learning in machine learning happens. Take a look at the GIF on the page. We'll begin with every point on the training set at the top of the tree. These training sets have labels. The red points represent students that did not get an A on the test, and the green points represent students that did get an A on the test. We decide to split the data into smaller groups based on a feature. For example, the feature could be something like their average grade in the class. Students with an A average would go into one set, B average another, and so on and so forth. Once we have these subsets, we repeat the process. We split the data into a subset again on a different feature. Eventually, we reach a point where we decide to stop splitting the data into smaller groups, and we reached a leaf on the tree. We can now count out the labels on the data on that leaf. If unlabeled points reach the leaf, we would classify it as the majority label. We can now make a tree, but how do we know which features to split the data with? After all, if we started splitting the data based on number of hours of slept before the night of the test, we'd end up with a very different tree that would produce very different results. How do we know which tree is best? We'll tackle this question soon. So as we watch this GIF here, we're first splitting them into average grade. Then we're splitting them again based on the number of hours slept. Then we're basing it on hours studied. And we can kind of get an idea of what we're looking at. Okay, implementing a decision tree. To answer a question posed in the previous question, we're going to do things a little bit differently in this lesson and work backwards. We're going to first find fit a decision tree to a data set and visualize it using the scikit-learn or scikit-learn data set or import, right? We're going to then use a systematically way to unpack the following: how to interpret the visualization tree, how scikit-learn's implementation works, what is Gini impurity, what are parameters and hyperparameters of the decision tree model, etc. We're going to use a data set about cars with 6 features: the price of the car, cost of maintaining it, number of doors, number of people the car can hold, the trunk size, and the safety rating. So we've imported the data set into the workspace. Take a look at the first 5 rows of the data set by uncommenting print dot. So this one right here, we'll uncomment just to take a look at the first 5 rows in the data set. Looks like something like this. So looks like the price of the car can be very high, high, medium, or low. Maintenance can be very high, high, medium, or low. Number of doors, 2, 3, or 4, or 5 more. The number of people it can hold, which can be 2, 4, or more. Lug boot, which can be small, medium, or big. And then finally, safety rating, low, medium, or high. So it says we've created dummy features for the categorical variables set in the predictor. Target variables X and Y representatively. Uncomment the lines pertaining to this and press run. So setting the target and predictor variables, it wants me to uncomment these lines here. And we'll get an idea of what exactly we can also examine it by printing X columns. We can do this by uncommenting once again. And we get an idea. I am going to end up commenting the head because we kind of get an idea of what that is doing, what this is right here. So let's uncomment this and see this instead. In this, we have all of the different variables, and it looks like there's 21 columns. So there are 21 columns that it can be. We've created the dummy variables as we said we were going to do. And boom. Okay, next. We're going to interpret a decision tree. We're now going to examine the decision tree we built for the car data set. The images to the right of the code editor is the exact plot you created in the previous exercise. Two more important concepts to note here is the root node is identified at the top of the tree. This is notated already with the number of samples and the numbers in each class that was used to build that tree. Splits occur with true to the left, false to the right. Note if the right split is a leaf node, i.e. there are no more branches. Any decision ending here results in the majority class. The majority class here is on UNACC. Note there is a term called genie in each of the box that is immensely important for how the split is done. We'll explore this in the following exercise to interpret the tree. It's useful to keep in mind the variables that we're looking at are categorical variables that respond to the ones that we detailed. Excuse me. The root node is identified at the top of the tree. This is notated already with the number of samples and the number in each class, i.e. unacceptable versus acceptable, that was used to build the tree. We've created a variable called frac_acc to print the fraction of acceptable cars to the tree was trained on. Calculate this from the root node of the tree. So it says it's created this right here. Right? So it wants us to look at this right here on the right hand side, and it wants us to calculate this from the root node of the tree. So the root node is identified at the top of the tree, which is this right here, right? This is notated already with the number of samples right here, 1,882, 382. And the numbers in each class, i.e. acceptable versus unacceptable. Class value looks like 970 versus 100 or 412 used to build the tree. We've created a variable to print the fraction of acceptable cars the tree was trained on. So the fraction of acceptable cars is going to be value 0 divided by value 1. Interesting. What does it want me to actually do? It just wants me to actually calculate it. I see, not using this obviously, but 412 is pulling from the acceptable. So apparently acceptable is unacceptable is first, and then we divide that by the number of total samples, 1382. The first split occurs off the root node based on the Boolean safe low is less than 0.5. As this is a dummy variable, a value of 1 indicates safety is equal to low, 0 indicates safety is low. Split occur with true to the left, false to the right. Note that the right leaf is a leaf node. There are no more branches, so any decision ending here results in the majority class. What is the predicted class of any variable with low safety? So for the class, I would assume that it's unacceptable. I'm just confused exactly what it wants me to do. When safety is low, this intuitively makes sense because, right. So that's what I would assume. had to throw it in some parentheses, right? Identify the final outcome of the decision tree for the example when buying car very high is equal to 1, persons equal to 2. We define a variable called sample class. So we're saying that the buying is very high. So when we come here, we have that the buying very high is equal to 1. So it's going to say this is not true and instead go here probably, if I had to guess. This tree is not making a lot of sense. There's no like arrows or anything like that, but sample class, I would assume this would also be unacceptable. Yeah, class should be equal to unacceptable. Cool. Gini impurity. Consider the two trees below. So which tree would be more useful as a model to try to predict whether someone would get an A in the class? Obviously, I'm going to say this one right here is going to be a little bit more useful, as it's clearly defining which variables are which. Let's say you use the top tree, you'll end up at a leaf node where the label is up for debate. The training data has labels for both classes. If you use the bottom tree, you'll end up with a leaf with there's only one type of label. There's no debate at all. We're much more confident in our decision if we use the bottom tree. Good. This idea can be quantified using the Gini impurity of set of data points for two classes, 1 and 2, with probabilities P1 and P2 respectively. The Gini impurity is this. The goal of the decision tree model is to separate the classes the best possible, i.e. the minimized impurity or maximize the purity. Notice that if P1 is equal to 0 or 1, the impurity is 0, which means there is only one class, so there is perfect separation. From the graph, the Gini impurity is maximum at P1 is equal to 0.5, which means the two classes are equally balanced, so this is perfectly impure. In general, the Gini impurity for class C is defined as 1 minus the sum of the probability squared. Using the same decision tree from the previous example, notice that each node is labeled with Gini equals. Right, it has Gini equals on the right here, which is the Gini impurity for the samples of that node. For the root node, calculate the Gini impurity using the formula and confirm this matches the value listed on the node. So it wants me to, for the root node, which is up here, it wants me to calculate that Gini impurity. So to do that, we have this Gini root. Okay, so we want to do it by saying 1 minus, and then we have probability of 1, value of 1 squared. So that's going to be that 970 divided by 1382 to the power of 2 plus 1 minus this same one, right? And then this is also squared. One minus did I do that right? It says my root node one is 0.418. That's exactly what I got, so it looks like I did it correct. Confirm the Gini impurity for the bottom left node, which is this one right here. Since this is a non-root node, either a leaf or a split node, the Gini impurity is only calculated for the samples passing through this node, not the entire data set. Hence, the numbers of samples is 449, not 1382. So it wants me to do basically the same formula here. In the first one, though, instead we're going to do 96 divided by the actual samples, which is 449. And then we'll do the same square method here and then add a plus. And then We'll do this same 96 divided by 449 to the power of 2. Didn't end up getting that one correct. We're looking for a Gini purity of 336. Use the same formula as above, but observe that the bottom left node has 96 and acceptable answers, so P1 is equal to that. And that's exactly what I thought I did, but perhaps not. It's because I didn't do 1 minus. 1 minus. There it is. Perfect. So a little mistake there, but we should be all good. Just remembering our 1 minus, right? Information gain. We know that we want to end up with leaves with low Gini impurity, but we need to still figure out which features to split on in order to achieve this. And to answer this question, we need to calculate the information gain of splitting the data on a certain feature. Information gain measures the differences in the impurity of the data before and after the split. For example, let's start with the root node of our car acceptability tree. That's this. The initial Gini impurity, which we have confirmed previously, is 0.418. The first split occurs based on the feature safety low is less than 0.5, as this is the dummy variable with values 0 and 1. This split is pushing higher safety cars to the left, 912 examples, and lower safety cars to the right, 470 examples. Before we discuss how we decided to split on this feature, let's calculate the information gain. The new Gini impurities for this split node are now 0.495 and 0, which is a pure leaf node. Altogether, the now weighted Gini impurity after the split is equal to 0.3267. Not bad. We want our Gini impurity to be lower. This is lower than our initial Gini impurity, so by splitting the data in a way, we've gained some information about how the data is structured. The data sets after the split are purer than they were before the split. Then, the information gain or reduction in impurity after the split is that. The higher the information gain, the better. If the information gain is 0, then splitting the data on that feature was useless, right? That makes sense. Verify splitting on a pure node will result in an information gain of 0. For example, with the right-hand side split of the root node, safety low is false. Consider the further split of the node. The result will be the subsequent split behind. We'll still have a Gini impurity of 0. Fill this code editor and uncomment the relevant lines to calculate the Gini impurity. So for number 1, information gain at a pure node, we can say this and that. In line 4, an uncommented node here. So we want to do the 1 minus, and then we'll calculate the first one, which in this case it's the 470 divided by 470, which is just 1, and then we do the same formula as before, which is then we add 1 minus 0, right? And we are going to end up, like it doesn't really matter, but we're going to do it anyways. We're going to square both of these variables, right? 0, and this leaf contains only 1 class, right? So that's what I'm thinking I'm supposed to be doing here, right? Oh, it just wants me to put 0. Okay. Cool. Calculate the information gain on the next split on persons 2 in the tree, but reading the following. The number of samples of the tree, the input to split ratio are persons 2, the initial Gini value at the parent node, persons 2, initial Gini's persons 2, the Gini value left and Gini value right node, and this input uncomment the relevant lines of the code, and press run to obtain the information gained at this split. So we're going to have to fill this in. I'm just going to get the hint for this one because I know it's just going to be a bunch of numbers here. 604 divided by 912. Let's see where we got that. We ended up getting that from 604. I actually don't even see a 604. Calculate the information on persons 2 in the tree. Persons 2 is right here. So we have the 604. I'm not exactly sure where we're grabbing 604 from. Because typically we'd be grabbing one of these two numbers, dividing it by that 912. I see where the 912 comes from, but I'm not exactly sure. 0.434, and then 0, and then 0.495. 1 second, y'all. That's crazy. So let's continue on here. Sorry about that. How a decision tree is built, feature split. We are ready to understand how the decision tree was built by scikit-learn. To recap, the root node in the tree is the top part. We've been using so far to split is the feature safety low. When its value is 1, this corresponds to the right split. Vehicles with low safety, and when its value is 0, this corresponds to the left split. Information gain is the difference in the weighted Gini impurity before and after split at the node. We saw in the previous exercise this information gain for safety low as root node was 0.4185 minus 0.3267 is equal to 0.0918. We now consider an important question. How does one know this is the best node to split on? To figure this out, we're going to go through a process of calculating information gain for other possible root node choices and calculate the information gain from each of these ones. This is precisely what is going on under the hood when one runs decision tree classifier in scikit-learn. Guys, scikit-learn is just OP. We've learned it. They are absolutely goated. By checking information gains of all possible options, the algorithm decides based on the best feature to split at every node. For starters, we'll consider a different feature we could have split on. First, persons 2. Recall that persons 2 can take a binary value of 0 or 1 as well. Setting persons 2 as the root node means that the left split will contain data corresponding to a person 2 value. The right split will contain data corresponding to a persons 2 value of greater than 0.5. We define two functions. The first one is that helps us calculate Gini impurity and information gain in the code editor. Read through the functions and see how they reflect the formulas we have covered thus far. Using the functions, we're going to calculate the information gain by splitting on persons 2. We can then follow this procedure for all the possible root nodes and check if the feature safety low is indeed our best choice for this. So we're going to create two data frames left and right that present the y-train values and that correspond to x-train persons 2 being 0 and 1 respectively. Calculate the length of these data frames, store them as len length and or len left and len right, and then print them. So it wants me to first calculate the sample sizes, right? So len left is equal to length of, we have the data here as represent the y-train values that correspond to x-train. So we have two variables, current impurity. I assume we would use the info gain definition here, but no, it's saying y-train sub. What is this? I'm honestly a little lost on this info trees thing. I've always been told in other statistics classes, also my mind is elsewhere sometimes, obviously, as you have seen with this one, so I'm not at my best learning state ever here, but I always felt that the trees is a way of kind of trying to teach it in a way that if someone never knew what statistics were, you'd be able to explain it to them using like a tree. Or something that they could follow, but I always felt that it was like kind of a little tedious to do a tree, as it's typically more steps and stuff like that. I'm just kind of confused at exactly what I'm doing here. I don't know why I'm creating subs of the safety low feature. If anybody in the comments wants to comment out why I'm doing this, that would be quite helpful. I'm not exactly sure. Oh, and that's lovely, and it's because I didn't do that. Len left, Len right. Wait for... Yeah, I'm just a little lost when it comes to this stuff, and there's a lot to it, and this can definitely be something that's useful, but I just feel like, I don't know, maybe not the most useful tool. I could definitely be wrong, right? I could just be, I'm a little lost here, but it wants me to create two data frames, left and right, that represent the Y train values, and left train values that correspond with X train persons 2 being 0 to 1 respectively, and store them as the length and then print them. So let's take a peek at the solution and see what they ended up doing here. So we have oh yeah, this is read only. So then we have right and left equal to Y train, and Y train equal to 1 and 0, and then I just don't understand what this is saying in the hint. I can do this though. We'll say that left is the 0 column, right is the 1 column. We'll change this to Y train, change this to 1. Then we'll get len left is equal to len of left. And then finally, len of right is equal to len of right. And then it wants me to print them, so I'll end up... okay, instead of this, does it want it to be persons? I assume it wants it to be persons 2 perchance. Yeah. There we go. We're now going to calculate the Gini impurities corresponding to the overall training and data and the left and the right split. To do so, uncomment the line pertaining to Gini impurity calculation. For the Gini value of the left node, create a variable called Gini left and use the Gini function to calculate the value. So we'll do that by saying Gini left is equal to Gini function with the data set of, left. And then I assume we'll make a Gini right and do the Gini function on the right data. Cool. Before proceeding to calculate the information gain on the split, let's consolidate what we've calculated in the previous checkpoints. There are 917 cars with 2 persons with a person 2 value of 0 and 465 cars with a person 2 value of 1. The overall Gini impurity in the training data is 0.48185. The Gini impurity for the left split was 0.4949. The Gini impurity with the right split is 0. That means the weighted impurity of all this is this. And this information gain for a tree whose node is persons 2 should be this. Use the info gain function to calculate the information gain corresponding to this split and sort in info gains person 2. Print it to check if you did in fact find the actual thing, right? So we can do, we can uncomment all these print lines, right? They've put these nice, very kind print lines. But it wants us to create a info gain persons 2. Set it equal to the info gain function, and that takes a left data, so I'm going to call the left function the right data, and then current impurity. with the, I would assume it's just GI as the current impurity. Could definitely be wrong there. Nope, not wrong. And then 4, we've now verified that splitting at a root node of person 2 gives us a letter information that's splitting at safety low. Verify the information gain at the highest node using info gain and looping through all the features, uncomment the lines that pertain to this calculation to verify if the tree has been working. Okay, so we have the ability here to comment out all these lines. And hopefully this just works. And it does. So now we can see all of the information, and I assume whatever gives us the highest value here is going to be the most useful. So it looks like the safety low features give us the highest value, so that's what we have been doing. Okay, how a decision tree is built via recursion. Now that we can find the best feature to split the data set, we can repeat this process again and again to create the full tree. This is a recursive algorithm. We'll start with every data point in the training set, find the best feature to split on, split the data on that feature, and then recursively repeat the process again on each subset that was created from the split. We'll stop the recursion when we can no longer find a feature that results in any information gain. In other words, we want to create a leaf on the tree when we cannot find a way to split the data that makes purer subsets. Up-to-date variables ytrans sub and xtrans sub with a logical filter to represent the data at the left node and right node split. Note this will include only the data that has been split on the root node to the left, i.e. safety low is equal to 0. Or is less than or equal to 0.5. Okay, so it wants us to uncomment these lines right here. And instead of having, so it wants us to update these two variables here with a logical filter to represent the data at the left node after the root split. So for the left node, I'm actually so confused. Like this is the same exact hint that it gave us before. What happens when we just run the code? I did not update him. Let's take a peek at the solution here and see what it exactly wants us to do. I'm so confused by this. It just looks like everything's uncommented. That's literally the only difference. So, I suppose I will uncomment all of this and see what happens. This is literally the only difference from the example solution, so I'm very confused why they're not actually having me do anything besides just uncomment stuff. Train and predict using, this is what's going to be a little bit better and more useful if we want to use decision tree stuff, right? Let's talk about scikit-learn. Now we finally built a decision tree ourselves. We'll use scikit-learn's tree module to create, train, predict, and visualize a tree decision tree classifier. The syntax is the same as the other models in scikit-learn, so it should look very familiar. First, an instance of the model is instantiated with decision tree classifier. To use non-default hyperparameter values, you can pass them at this stage, such as decision tree classifier max depth is equal to 5. The fit takes in a list of data points followed by a list of labels associated with the data and build the decision tree model. Finally, we can use the predict method. This is very similar to what we've been doing before. And we can then use predict prob A, can also be used to return a class of probabilities instead. Last, .score can be used to generate the accuracy score with a new set of data and labels. As with other sklearn models, only the numeric data can be used. Category variables and nulls must be handled prior to model fitting. So let's create a decision classifier. So we're going to call it dtree. And we're just going to call it decision tree classifier with default parameters. Print the parameters of the tree using the getParams method. So if I do dtree.getParam, I definitely have some spelling error here. Decision, is that what it is? Yeah, decision tree classifier. Cool, there are all the tree parameters. Then fit dtree using the training data and labels. So we'll do that by doing dtree.fit, and we're going to be fitting it to the training data set and labels, which it looks like is x train, y train, and then in here we'll have dtree.getDepth. Looks like the tree goes 11 deep. Predict the class of the test data set. So we'll do y prediction is equal to dtree dot predict based on x test data. And then it wants us to print out the score by doing dtree.score with our y prediction variable. X test. It wants us to do x test y. Oh, we actually want to do y predicted actually. So (1.0) makes me think that this is I'm doing something wrong here. It actually does want me to do y. Because then that gives us a 98% accuracy. Finally, visualizing decision trees. Great, we built a decision tree using scikit-learn and predicted how to new values with it, but what does that tree look like? What features can you use to split? Two methods only scikit-learn and matplotlib can help us visualize the tree. First, using treeplot. The second, listing the rules as text. There are other libraries available with more advanced visualization. GraphViz or dtreeviz, for example, may require additional installation but won't be covered here. Let's run on the existing code and inspect the current output of tree.plotTree. Use the arrows of the in the browser to zoom out for a closer view. What seems to be missing? The features are labeled only by index rather than by name. Pass the additional parameter feature names is equal to that to the plotting function and note the differences. So it wants me to go into this and we'll add in these additional features to the feature names is equal to xtrain.columns, class names is equal to unacceptable versus acceptable, and then filled equals true to the plotting function and see what happens. And that's very nice. Now we get a nice coloring. We can see it a little bit better. We get the actual values of the, we get the actual names of the columns, which is very nice. So perfect. All right, decision tree advantages and disadvantages of we've seen already. Decision trees are easy to understand, fully explainable, and have a natural way of visualizing the decision-making process. In addition, often little modification needs to be made to the data prior to modeling, such as scaling, normalization, removing outliers, and decision trees are relatively quick to train and predict. However, now let's talk about some of their limitations. One problem is they're currently making our decision trees is their trees aren't always globally optimal. This means that there might be a better tree out there somewhere that produces better results, but wait, why do we go through all that work of finding information gain if it's not producing the best possible tree? Our current strategy of creating trees is greedy. We assume that the best way to create a tree is to find the feature that results in the largest information gain right now and split on that feature. We never consider the ramifications of a split further down the tree. It's possible that if we split on a suboptimal feature right now, we would find even better splits later on. Unfortunately, finding a globally optimal tree is a difficult task. Finding a tree using our greedy approach is reasonably a reasonable substitute. Another problem with our tree is that are prone to overfit the data. This means that the structure of a tree is too dependent on the training data and may not generalize well to the new data. In general, larger trees tend to overfit the data more. As tree gets bigger, it becomes more tuned to the training data and loses more generalized understanding of the real-world data. Fit the two decision trees to the dataset we've been working with. D-tree1 with no restriction on the max depth. D-tree2 with a max depth of 7 on the training data. Print the max depth of each tree. So we have two decision trees here. So we'll say that this is equal to decision tree classifier with no arguments, we're going to say, but this one is going to be decision tree classifier with one argument, and that is max depth is equal to 7. It's not going to be the keyword. Yeah, actually, I did do that right. Did you fit the first decision tree to the training data and print its depth? Okay, so no, I did not. So if we do tree depth is equal to tree1 dot what's the code for it? Get depth. Okay, cool. Get depth. And did you fit the decision tree? Oh, we have to fit it first. dtree1 dot fit to the x train y train data, then get the depth of that data. Next, we're gonna fit the second one. So we'll do dtree2 dot fit with x, the x train and y train data set. And right now the depth we're saying is equal to dtree2 dot get depth. Did you calculate the accuracy score? Oh. On each tree. Oh, okay. So we want to do dtree1 dot score based on the x test and y test data, and then we'll do dtree2 based on the same stuff, the x test and the y test. So when we had a maximum depth of 7, it looked like our accuracy was 96%, but when we said go wild, no max depth, it ended up going 4 more trees deep and ended up having an accuracy of 98%. All right, we got some questions here. The following tree was built on the IMB attrition data set, predicting what employees will stay or leave within the year. What is the predicted value for an employee with num companies work 5, total working years equal 2, distance from home equal 5, and age equal 22? What is the gene impurity of the final leaf? So it first says total working years greater than or is less than 2. That is true, so it's going to go this way. Distance from home less than or equal to 7.5. That is true, so it's going to go this way. Age is less than or equal to 24. It's true, so it's going to go this way. So now we have this variable here, and it's asking what the Gini impurity level is, and I'm going to say it's this one right here. So it says they're going to quit, and yeah. Why is the algorithm used to construct decision trees considered a greedy algorithm? Basically, it doesn't look ahead. It chooses to split the data based on the current data set. Right, exactly. What are the following data sets as the smallest Gini impurity? I would say that 1 minus, so it would be this one, right? Yeah. Which of the following statements about decision tree implementation in scikit-learn is true? The differential criteria using math always results in the best tree. That's not true. Max depth criterion impurity min low tuned to better tree performance. Setting min impurity decreases the tree will never stop being built. I'm going to say this one just because it said it can result. Suppose the following binary information are available in a data set to predict employee attrition. The information gained for each is computed in the table on the initial data set. What is the first split in the tree? The first split is going to be likely department research and development. It looks like that's the largest one at 0.0045. I'm going to say, never mind. There's actually, that's not an option. In that case, it's going to be, is it not where, it's because I didn't look. Business travel frequently. 43, 45, 04, 49, 44. It's right here. My gosh, I didn't see it. The following tree was built on the IMB attrition dataset, predicting what employees will stay or leave. What is the initial Gini impurity on the dataset, stay versus quit? So initial is, let's split maximize the information gain on the set. It's the initial one, right? So total working years at this value, the root. Fill in the code to fit a decision tree classifier. So first, we want a max depth of 5. So we're saying max depth of 5 is going to go inside the decision tree classifier. We're going to fit it to the training data, so xtrain and ytrain, and then we're going to score it based on the testing data. That makes sense to me. Perfect. The following tree, again, built on that IMB or IBM data set. What is the information gain when splitting on the node age is less than or equal to 24? We end up gaining no open image and tab for better visualization. This one I'm not exactly sure on. What is the actual information gain? When we do this, it's likely something where you subtract. I'm going to say it's this one right here. It was this one. Remember, the information gain is the difference in the initial Gini impurity and the weighted Gini impurity after. So it would have weighted. I'm not going to sit here and wait it out and waste your time. What does scikit-learn's decision tree classifier .fit method do? The .fit method creates a decision tree. Nope. Method returns the accuracy. Nope. Creates a random forest of decision tree classifiers. The fit method creates a tree according to the training. Yeah, this. 88%. Not going to complain too hard on that. Find the flag. So we have a bit of a thing right here. Shouldn't be too hard, hopefully. So the data set has been loaded for you in script.py and saved as a data frame in df. Some of the input and output features are this. We want to build a decision tree classifier to predict what continent a particular flag comes from. Before that, we want to understand the distribution of flags by continent and calculate the amount, the count of flags by using the landmass value. Okay, so there's 15 total things. Honestly, guys, I'm going to skip this project. I usually don't skip projects because I think they're super helpful, but I don't imagine that we'll be using this method of building decision trees quite often. I feel like it's kind of this one-off video where we're going to be going through decision trees. I mean, we've literally been doing regression basically all of this chapter. We're going to be getting into some like algorithms and stuff. I just don't think decision trees are going to be that important. So I'm not going to waste your time with a project here. I am just going to go through quickly though and exit or check them all off so that we can continue. The thing with projects is they're 100% up to you if you want to do them. So I'm going to continue on though, and we're going to, in the next video, talk about normalization, which is something that's very, very useful, obviously. If you did enjoy this video, please be sure to leave a like, subscribe, and I will see you in the next one. Peace out.